Hey everyone, welcome to Simply Learn's YouTube channel. In today's session, we will be discussing about interesting topics in C Sharp, that is trees and graphs in C Sharp. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So, if you're a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and hit that bell icon to never miss an update from Simply Learn. In this tutorial, let's understand what exactly is the agenda. First, we will see the importance of trees and graph data structures in C Sharp. After that, we will go over the basics of trees. Later, we will look at the different types of trees in C Sharp. Following that, we will look at some basic tree operations and terminologies. Moving ahead, we will look into the tree traversal, and finally, in tree data structure in C Sharp, we will look at some tree-related applications. Following on from the tree data structure, we will learn about the graph data structure in C Sharp, beginning with an introduction. After that, we will look at the various types of graphs, as well as some basic operations that are performed in graphs. Following that, we will learn graph terminology and then look into graph traversal. Next, we will look at how we can represent graph data structure, and then we'll look at some important real-world examples of graph data structures. Let's start with the basics and try to understand the importance of tree and graph data structures in C Sharp. The tree and graph data structures in C Sharp are critical for modern programming. Each of these data structures is used to construct a model of real-world problems, which are then solved efficiently using this model. After understanding the importance of tree and graph data structure, now let us understand the tree data structure to proceed with the introduction. The tree is an hierarchical data representation format. Each node in a tree has two components, data and references. The top node of the tree is known as root node, and the two products beneath are known as the left subtree and right subtree. Also, they are called as children. Let's look at the real-world example of a tree data structure. An organization structure that functions as an hierarchy. So, here's an example of how an organization where the CEO works as the root of the tree hierarchy of the organization. Then we have children, that is CEO and CFO, which are the Chief Financial Officer and Chief Technical Officer. And we also have CMO, that is Chief Marketing Officer. Then we have children of CFO as Financial Assistants and CTO as Software Engineering. And finally, we have Social Media. Following this tutorial, we will look at the various types of trees. So there are only 5 types of trees: the general tree, the binary search tree, the AVL tree, and the red-black tree, which is the final or 5th type of tree. Let's look at all of these different types of trees by defining them all. We have the general tree first. When no constraint is imposed on tree's hierarchy, it is referred to as general tree. Each node in the general tree can have an infinite number of children. This tree is a superset of all other trees. We also have a binary tree. A binary tree is a tree where each parent can have no more than 2 children. The children are referred to as either the left or right child, one of the most widely planted trees. The binary search tree is the next type of tree. Binary search tree is a binary tree extension with some additional constraints. In BST or binary search tree, the values of a node left child must be less than or equal to the value of its parent, while the value of node's right child is always greater than or equal to the value of its parent. The binary search tree property makes it suitable for searching operations because we can determine whether the value will be in the left or in the right subtree at each node. The 4th type is the AVL tree. The AVL tree is a binary search tree that self-balances. The acronym AVL is derived from its creators, Adleson, Welshi, and Landis. This way, the first tree that was dynamically balanced, each node in an AVL tree is assigned a balancing factor which is used to determine whether the tree is balanced or not. In an AVL tree, the heights of the node's children differ by no more than 1. The AVL tree, the valid balancing factors are 1, 0, and -1. Finally, we have the red-black tree. Another type of self-balancing tree is red-black. The name red-black comes from the fact that each node is a red-black tree is either painted red or black based on the red-black tree properties. This ensures that the tree maintains a balance. Following that, we will look into some basic tree operations. So first and foremost, we have an insertion operation in the tree. Let us try to define it. Insertion in a tree can be accomplished in various ways, depending on where the new element is to be inserted. Following insertion, we have deletion operation performed on a tree. When it comes to deleting a node in a tree, it can get a little tricky when you consider what to do with the node's left and right children. Finally, we have a searching operation and are attempting to understand it. When searching for an element, determine whether the current node's value matches the given value and then recurses to the left and right subtrees, repeating the process. Following that, we will learn about tree terminologies. So here are tree terms which are used in this tutorial. A root node is the first node from where the tree sprouts as in A. An edge is connecting link between any two nodes. AB and AC are the examples in the picture. Following that, we have a parent node H, which has a branch from it to another node. A children node or a child node J, K and L is a node that is a descendant of another node. Each child of a node forms a subtree recursively in a tree. Next, tree structures store a set of values known as keys. Example B. Following that, the sibling node is on the same hierarchical level as the parent node D and F. After that, the total number of children of a node is its degree. Following that, the total number of edges that lie on the longest path from any leaf node to a specific node is the node's height. A leaf node is a node that does not have any children. Each step from top to bottom in a tree is referred to as a level of a tree. Next in this tutorial, we will learn about traversal in the tree data structure. So in general, we have two types of tree traversal. First, we have a breadth-first search. The breadth-first search algorithm traverses or searches tree data structures. It begins at the tree's root and explores the neighboring nodes first before moving on to the neighboring at the next level. And depth-first search can be used for second tree traversal. Depth-first search is a tree data structure traversal or search algorithm. Starting at the root, one travels as far as possible along with branch before returning to the root. Depth-first search tree traversal has been classified into three modes of traversals. So we have pre-order traversal, in-order traversal, and post-order traversal. Let us try to define all these traversal in greater detail. For example, in pre-order traversal, we first visit the root node, then the left subtree, and finally the right subtree. For a better understanding, consider the following example of pre-order traversal. Next, we have the in-order traversal, which means that in this type of traversal, we first traverse the left subtree, then the root node, and finally the right subtree. So for a better understanding, here is an example for in-order traversal. Finally, we have the post-order traversal. In post-order, we first traverse the left subtree, then the right subtree, and finally the root node. For a better understanding, here is an example of post-order traversal. Let us look at code demonstration for tree traversal with pre-order, in-order, and post-order. In this program, we first define a tree node as node 1 with values left and right, and then we define a show function to display all the tree traversals, and in this function, we defined a value in square brackets. Following that, we created a tree in which the root node is null initially. Then we have a function, namely return root, where we will return the root value, and finally we have the insert function, in which we create a new node and insert x value to that new node. After that, we have a condition that says if the root node is null, we will assign the new node as the root node. Otherwise, the root node will be assigned as the current node, defining the parent node. Following that, we assign the current node to the parent node with the condition that if the assigned value x is less than the left node, we assign that value to the left node, and if the left node is null, we will assign a new node to that left node. And the right node. If the assigned value x is greater than the left node, we assign that value to the left node, and if the left node is null, then we will assign a new node to the left node. Now, we will define all three tree traversals. First, we'll have to do pre-order traversal, which means that if the root node isn't null, the first will give the root node. And we will prefer to traverse first the left node, then the right node. Next, if the root node is not null, we will call to traverse the left tree, enter the root value, and call pre-order to traverse the right tree. Finally, in post order, we will call post order to traverse the first left and right tree and then assign the root value if the root is not null. Finally, we created a binary search tree in the main function, then call it the insert function to insert all the values. Finally, we will call the in-order function to perform in-order traversal followed by the pre-order traversal, and finally we'll call post-order function to perform post-order traversal. Now let's quickly try to execute the program and see the output. There you go. The program got successfully executed and we have all the three types of traversals: in-order traversal, pre-order traversal, and post-order traversal. Now let's get back to the slides. Now the next topic is the applications of trees. We have 5 applications of tree data structures in C#. The first application is the XML parser, which employs the tree algorithms. The tree's second application is a decision-based algorithm based on the tree algorithm used in machine learning. The tree data structures are also used in databases for indexing. The third application of trees. The following use of a tree data structure: domain name servers also use tree data structures, that is DNS. The fifth and final application of tree is File Explorer, Mobility, Computer, any computer BST in computer graphics. After understanding the tree data structure in C#, we will now try to understand graph data structures. The graph data structure is one in which data is stored in a network of interconnected vertices, nodes, and edges, also called as paths. As a result, a graph data structure that is made up of a set of vertices V and a set of edges referred as E or paths P. Consider the following real-world example of a graph data structure. Some websites such as Wikipedia, Facebook, and YouTube have many incoming links, whereas many smaller websites may have very few incoming links. We will look at different types of graphs. So there are generally 6 types of graphs. So first we will have directed graphs, next we have undirected graphs, weighted graphs, unweighted graphs, and finally cyclic and acyclic graphs. Let us try to comprehend all these graphs in greater depth. First and foremost, we have directed graph. Edges in a directed graph have a direction. The edges denote one-way relationship as each edge can only be traversed in one direction. Next, edges in undirected graphs do not have a direction. Each edge can be traversed in both directions, indicating a two-way relationship. A weighted graph is defined as if the edges in your graph have weights, your graph is said to be weighted. Next, we have unweighted graph, which is defined as a graph that is said to be unweighted if the edges do not have any weights. After that, acyclic graph is a directed graph in which at least one node has a path back to itself. The last type of graph is an acyclic graph defined. An acyclic graph is a directed graph with no cycles, meaning that no node can be traversed back to itself. In this tutorial, we will see some basic operations performed on graphs after learning about various graph data structures. So first we have the add node operation, which is used to add vertices to graphs. Next operation we did in the graph was to remove node, defined as remove node, removes graph vertices. The third operation is the add edge state, which establishes connections or paths between graph vertices. The fourth operation is remove edge, which is a function that removes connections or paths between vertices and graphs. Following that, perform a check operation to see if a graph contains a specific value. The sixth and final operation carried out in the graph has edges define whether or not there is a connection or path between any two vertices in a graph. After understanding some basic graph operations, we will look at graph terminology. First, a vertex is defined as a vertex or node is a name given to each data element. Next, we will go over edge, graph terminology. It is a connection between two nodes or vertices. Each edge has two ends denoted by starting vertex and ending vertex. The number of edges in a graph connected to a vertex is then defined as a degree. The total number of connected incoming degrees to a vertex is defined as in degree, while the number of outgoing edges that connect to a vertex is defined as out degree. Then there's a self loop, which is defined as If the two endpoints of an edge coincide, it is referred as a self-loop. Finally, we have an adjacency stage, which means that if an edge connects with two vertices, they are adjacent. In this tutorial also covers the graph traversal, which has two types of tree traversal. So the first one is breadth first search. Breadth first search is the first graph traversal we have. So BFS is an abbreviation for breadth first search. It is also known as level order traversal. The queue data structure is used for breadth first search traversal. Any node can be considered as a root node when traversing a graph with the BFS algorithm. The second kind of graph traversal is the depth first search, abbreviated as DFS. In DFS traversal, the stack data structure is used, which operates on the LIFO or last in first out principle. The DFS traversing can begin at any node, and any node can be considered as a root node until a root node is not mentioned in the problem. Let's look at the code traversal of the BFS and DFS graph traversals. In this program, we define namespaces as graph traversal, then defined a class name as graph. We defined the vertex variable for the graph's vertex, and finally, we defined the adjacency list array for all vertices. After that, we have graph function object, native code, with v1 vertex in the parameter, where we assign v1 to the vertex and assign v1 vertices to our adjacency, then instantiate adjacency list for all vertices. After that, we have a loop from 0 to v1 vertices, where we assign the vertices to list of adjacency. After that, we added edge v1 to w1 to the adjacency list. Following that, we defined BFS traversal in a parameterized source variable as s1, in which we declared an array as a visited boolean data value. Then, as we know, we traverse the breadth first search with queue data structure, and if the source node is in the visited array, we enqueue the source node to the queue. Then we have a while loop through all the nodes in the queue, and if the queue is not empty, we will dequeue or remove a vertex from the queue and print it. And then we use for each loop to get all adjacent vertices of S1. After traversing the BFS, we will now traverse the depth first search in the graph. As we know, stack data structures are used to traverse DFS, so we created a stack with source node as S1 and push the first node as the source node itself. Then we have a while loop that goes through all nodes in the stack, and if the stack is not empty, we pop or remove a vertex from it and print it. And then we use for each loop to get all the adjacent vertices of S1. After that, we have a for loop that will run up to the last vertex in the graph and start printing all the elements in the adjacency matrix list. Finally, in the main function, we have a graph where we call the edge function and add edges to the graph, and then we print the adjacency matrix, and finally we print the breadth first search and depth first search starting from vertex 1. Now let's quickly try to execute the program and see the output. So there you go. The code got successfully executed and you have both BFS and DFS traversals from vertex 1. Now, let's quickly get back to the PPT. Following our understanding of graph traversal, we will look at some graph representations in C#. In computer programming, there are numerous ways to represent graph. Different representations have different properties, and what should be chosen depends on specific algorithm we want to use. In other words, we present the graph so that the operations performed by our algorithm are fast as possible. So the first graph representation is an adjacency matrix followed by an indices matrix and finally an adjacency list. Let us define all three graph representations in greater detail, beginning with the adjacency matrix. The graph is represented as square matrix with the position Gij containing the value of 1 if there is an edge from Vi to Vj. If such an edge does not exist, the value 0 is stored in the field Gij. If the graph is weighted, we record the weight of the edge and in the position Gij, and the matrix is called a matrix of weights. If there is no edge between two nodes, this matrix, a special value representing the infinity, is recorded. The adjacency matrix will be symmetrical if the graph is undirected. The next graph representation is an indexes matrix. A graph can be represented using an incidence matrix with the following dimensions. This matrix is filled with zeros, ones, and minus ones. The value 0 is used to represent a row edge that is not connected to a column vertex. The number 1 represents a raw edge connected as an outgoing edge to a column vertex. The number -1 represents a row edge connected as incoming edge to a column vertex. The last graph representation is the adjacency list, defined as in this representation, we keep a list of neighbors for each vertex in the graph. This means that each vertex in the graph has a list of adjacency vertices, an array of vertices indexed by the vertex number with each array element pointing to the singly linked list of these neighbors. Finally, in this tutorial, we will look at the real-world examples of graph data structures. So here are the 6 real-life examples of graphs. We have Facebook Graph API, and we have Google Knowledge Depth. We have Yelp's local graph. Following that, we have path optimization algorithm. We have Google Map platform, and finally we have Flight Network. Let us discuss all these applications in greater detail. Facebook Graph API is defined as Facebook's Graphs API, and it perhaps is the best example of graph applications in real-world problems. The Graph API represents our paradigm shift in large-scale data provision. Next, we have a knowledge graph, a graph-based representation of knowledge that involves linking data and graphs. It is still unclear what it can and cannot do. After that, Yelp gradually replaced the older Fusion API with Graph API. The local Graph API makes it easier for developers to integrate Yelp data and share great local businesses via their apps. After that, we have a path optimization algorithm. Path optimizations are primarily concerned with localing the best connection that meets predefined criteria such as speed, safety, fuel, and so on, or a set of criteria such as products, routes, etc. Next, we have Google Maps Next, we have Google Maps platform application of graph, defined as the Google Maps and Routes API, which are examples of classic shortest path API. This graph problem can be easily solved using edge-weighted directed graphs or digraphs. The last graph applications is Flight Network. So efficient route optimizations perfectly fit graph data structures for flight networks. Airport procedures can be efficiently modeled and optimized using graph models. Now with that, we have reached to the end of this tutorial on trees and graphs in C#. If you have any queries regarding any of the topics covered in this session, or if you need the code that we have executed in this particular session, then please let us know in the comment section below, and our team of experts will be more than happy to resolve all your queries at the earliest. Until next time, thank you, stay safe, and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.